Bismillahirrahmanirrahim. Today we shall talk about stability analysis of control system. Specifically, we shall talk about the Routh stability criteria, generating the Routh table, interpreting the Routh table, and then we will discuss about some special cases of the Routh stability criteria when we have a zero in the first column. So we see what is and why zero in the first column. And similarly, we can have the occurrence when we have a row in the a complete row to be equal to zero. So I just talk about the zero in the first column and the row. So this means that we will be dealing with some kind of the table in the row stability criteria. Coming back to the stability analysis, so we see that any system, um, any system, you see that any system, you say that this is a system. System G of S, and let's say that this system at the input we are giving some bounded input and in the form of some signal, and at the output, if we receive the bounded output, so we say that this is a bounded system. So the output at the moment is equal to y of s. So the total response, we already know that the total response of the system can be represented as the natural response in t plus and the forced response, which is also called the transient response, or you can also say that this is equal to what is the transient response plus the steady state response. So the stability of the control system is achieved when the transient response decays to zero. So this x t approach to zero as t approach to infinity. So we are left only with the steady state response of the system. So we have generally we have two methods to find the stability of the system. Both methods have is mirror. So the first method is called the Routh stability criteria. This is the first method. The second method is called the Routh locus method. So we are dealing with the output signal in the form of the complex domain S domain, and we already know about the S domain that this is the complex domain which has the x y axis. So x is the real axis and y is the imaginary axis. And we call it the S domain. So we talk about this in the previous session. That what is the S domain? So we said that it has the S is the alpha plus minus j omega. So or we can also say S can also be equal to what? S is equal to plus minus the alpha plus minus j omega. So this complex plane, you see that when we are talking about the system stability, then we divide this complex plane into three parts. The first part is called this one is this plane, the complete plane, which is called the right half plane, RHP. I can write RHP, right half plane. So right half plane, and then we have the another plane which is called the left half plane. This is called the complete plane is called the left half plane. You can also say at one side of the positive side of the imaginary axis and at the negative side of the imaginary axis. And the third one is the imaginary axis. This is the imaginary axis, which is the boundary. Actually, this is the boundary. So we can have three kind of the system. If all the poles, we are mostly interested in the pole locations, and we will see what is the pole from the mathematical equation later on. But those values for which the transient, what is called, for which this the response of the system become equal to infinity, we call it the poles of the system. And let me mathematically, let me say, write this one, that what is the poles of the system. So mathematically, we can say that the transfer function of the system, which is equal to the numerator polynomial divided by the denominator polynomial. So these are the ns is the polynomial, and ds is also the polynomial. So we can also write this in terms of the polynomial. So if you write this in terms of the polynomial, then we know that this is equal to b naught plus b1 is 1 plus b2 is 2 plus bm is power m divided by, then we can write this one as a naught plus a1 is 1 plus a2 is 2 plus an is power n. So we can say that the order of the numerator polynomial is m, and the order of the denominator polynomial is n, and the order of the system is equal to n minus m. Uh, um, um, the order of the system is the order of the denominator polynomial, but if we cancel the value of the s in the numerator, then this can be equal to the n minus n. That will be the order of the system. So we can write this in the polynomial in the root form also. So if you write this in the root form, so we have how many roots in the numerator polynomial? M number of roots, and then we have n number of roots in the denominator polynomial. So let's say this is equal to I equal to 1 to m and s minus zi divided by this is equal to I is equal to 1 to n s minus pi. So I write zi because any value of s in the this root. Let me cross this one. For any value of this s minus zi, for any value, when this become equal to 0, so g of s also become equal to 0. Similarly, when s minus pi become equal to 0, then g of s goes to infinity. So we say that for any root in the for any root of the denominator, the transfer function become equal to 0, and when it become equal to 0, we call it that root we call it to be the pole of the transfer function. So these are the zeros and poles. So mostly we are interested in the pole information because we say that the poles at all other location except the 0, because at the 0 it will give the force response or the steady state response of the final output function. We discussed this in the previous section, but the pole at any other location will give us the transient response, and we are interested to make the transient response equal to 0 so that we achieve the stability of the system or the steady state response of the system. So now you see, coming back to the this slide, and we say that for any pole, if they lie in the right half plane, over here in the right half plane in this side on the positive side of the imaginary axis, then we say that the system is unstable. So we say that the system is unstable. And if we are at the left hand side of the imaginary axis, then we are saying that the system is stable. And if we are at the boundary of the this imaginary axis, if we are at the boundary over this axis, the boundary of the left hand side and the right hand plane, then this is called the marginally stable system. Marginally means that it will give a bounded output, but for every bounded input, but it will not reduce to what is called, it will not come to the steady state position, or the error will not reduce, so it will remain the same. So the transition will not finish up in the partially balanced system, so it will give you a continuous like oscillating signal. Now, so we have these three type of the occurrences. So we say that even if you see that if we are in the left half plane and we know about the location of the if we say that all the poles are in the left half plane, then quickly we can say that it is a stable system. And if somehow we know the location of the or the position or the pole information of the poles, the information of the poles, even not the exact location, but if we know about the information of the poles, what kind of information? Suppose we have this complex axis S plane, and let's say that the poles, generally say that the poles are in the where the poles are located on the real axis here. So if the poles are located on the real axis, if it is this point, the two poles are located at the same point, or if the two poles are located far away from each other. But in this case, if it is on the real axis, we know that it can either be a critical dam system or over dam system. So we know about the zeta also, the response of the system also. But if we know that the poles are located on the what is called in the imaginary axis, we do not know about the exact location, but we know that it is available on the imaginary axis. Then we can quickly assume that it is an under dam system. So we can assume that it is an under dam system. So you see that we can say that the system is stable. It is in the left half plane. All the poles lie in the left half plane. But still, we can also assume that what should be the response of the system, but we do not know the exact position of the poles. So you see that if we know this information, we can find the stability information. So this kind of information is given by the Routh stability criteria. So what the Routh stability table is given, it is giving you the pole information. Sorry, the pole information in the right half plane or the left half plane. So it will give you this information. It can also give you the information related to the poles located on the real axis or on the complex axis. Pole information on real and axis and imaginary axis. So if the poles are in the left half plane and it is in the along the imaginary axis, then we say that it is a stable system, but it is under dam system. And if you say that the poles are in the left half plane, but it is along the real axis, then still we say that it is what it is in a critical. It may be a critical dam system or over dam system, because this is not giving you the exact location of the pole. So the pole locations, let me change this one. The pole locations, no information is given, not available. And that is why you do not find the exact system that what kind of the overall response should be. Anyhow, You see that still this route stability criteria can be used to find the stability of the system. And it can also show you the information whether the poles are lying in the left half plane or in the right half plane. So the another method was the root locus method, which will give you the complete information, the location information also. But we will discuss this in the next session, not in this session. One thing you should know that this root locus can also give you the range of values for which the system remains stable. So it can also be used for some design kind of the purpose also. So we should also remember this one. Later on, we can use this one also for design kind of the purpose. So the most important thing is to generate the um, what to generate the generating a route table. This is the most important. We just write that the transfer function of the system is equal to the numerator polynomial divided by the denominator polynomial. And we are interested in the denominator polynomial because this will give us the pole information. So let's say that the denominator polynomial is equal to what? Yeah, the denominator polynomial is from the same expression. So we said that an is power n plus a1 an minus 1 is power n minus 1 plus a2 is 2 plus a1 is 1 plus a0. So this is the denominator polynomial. And let's say we have this equation. Um, this equation, the coefficient can be plus minus also. It's not necessary that they all are positive. So we have, let's say that we have this what is called this equation. So we got this equation, and now we will form the route table from this equation. So what is the highest order? The highest order is s power n. So we will start with s power n. So we started with s power n, and so we started with s power n. And now let's see that the next row in same column, what it should be? It should be Sn minus 1. So s power n, and then the next one will be equal to s power n minus 1. So Sn, so we start with the coefficient of Sn. So the coefficient of Sn is equal to what? An. So it is equal to An. And then we'll come in this fashion, An minus 1, then in this fashion n minus 2, and then n minus 3, and then you see n minus 4, and then n minus 5, until what? Until you have a 2, and then you have a 1, and then a 0, and then 0. So this you will get only if n is even. For example, what? For example, if you have this, let's say that you have what? Um, Suppose the denominator polynomial is equal to what? It is equal to a 6. Or you can also use the values s power 6 plus a 5 is, let me use the values just for the example. Let's say that we have what? Denominator polynomial is equal to 1 is power 6 plus 2 is power 5 plus 4 is power 4 plus 3 is power 3 plus 7 is square plus 8 is plus 10. So we got this. So how to interpret this to form the initial table? So you see the highest order is 6, next is 5. So we start with the coefficient of is 6, which is equal to 1. and then the all other coefficient will be repeated is 2, nice 5. So coefficient this, then we have 4, then we have 3, then we have 7, then we have 8, then we have 10, and then we have nothing, so equal to 0. So this means that if any s with some power is 3 is not available, so it will become equal to 0, like this one. Remember this one. So suppose is 6 plus, then 2 is 5, then we have suppose is 3, then we have is 2, then we have s. Suppose if we get this kind of the equation, so how we will transform this one. So we have is 6, and then we have is 5. So S6 is 1, S5 has coefficient equal to 2, then S4 is coefficient of equal to what? 0, and S3 is 1, S2 is 1, and for S3 is 2, S1 is also equal to what? Is equal to 1, and S0 is equal to 0, and then this one is also equal to 0. So the constant term is also equal to 0 in this case. So you see that we can easily transform the information into the Routh table. Similarly, if you have the even number of the power is even, then what you will get? Then you will get the same kind of the equation, but the last two term will be changed. For example, how much? For example, this one. So see, this is same is power n, and then we have s power n minus 1. So a n, and then a n minus 1, then a n minus 2, then a n minus 3, up to where? If it is odd, then you will get a power is 3, then 2, then 1, then no. So this is the so we will finish up with this one. Suppose how? Suppose let's say that we have what? We have the denominator polynomial is equal to what? Is 5 plus is 4 plus 3 is 3 plus 2 is 2 plus 6 is plus 7. If we have this, so we can easily transform this information into the initial table, which is equal to what? Is we started with is 5, then is 4. So the coefficient of is 5 is equal to 1, is 4 is equal to 1, is 3 is 3, is 2 is 2, is 1 is 6, and is 0 is 7. So we started, and at the end you can also place these two zeros you like. So we form the initial table. So this is for the if we have the power of is odd, so we'll come up with this one, and if the power of the is even, then we'll come to the previous one, this one. So anyways, whatever is the power, so you can easily transform the information using this procedure. We start with the highest one, and then the next one, and then just put the coefficient in this specific order. So we get the initial table of the Routh table. So the initial table is formed. Now the next thing is how to form the what is called the next row. Let me come back to the, so we got this one, maybe this table or this even table, whatever. So we got to the position, this one. So let me write again the denominator polynomial ds is equal to what? A n is power n plus a n minus 1 is power n minus 1 plus a2 is 2 plus a1 is plus a0. And then we make the table. The table is what? So you have s power n and s power n minus 1. S power, sorry, this is n minus 1. And then we started with a n minus 1, then we have a n minus 2, a n minus 3, then we have a n minus 4, a n minus 5, and finally we reach to a 2, then we have a 1, and then we have a 0 and 0. So this means that this is for the even number of the power order. So when the power order is even. Now we are going to find the um, next row. So the next row will be equal to, you see, the power order will reduce in the same manner. So we have Sn, then Sn minus 1, then S minus n minus 2. So this is the order of the power of the is the exponential of the what is called the S. So the how to calculate the next entry. So we will calculate this, 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 this. Similarly, we have to calculate the next what is called the next row, which will be equal to Sn minus 3. Then we will calculate what S2 up to. Then finally we will come to S and then S power 0. So we will calculate all these. So the question is how to do this one. So the question is how to find this information, this question marks, these entries. So these entries can be easily filled by the procedure. What we have to do, we have to multiply this with this one, this entry. Similarly, we have to multiply what? We have to multiply this entry with this one and then divided by this one from where we started. So this will give us the next entry. So it will be equal to a n minus 1 multiplied by a n minus 2 minus, let me start again, minus a n multiplied by a n minus 3. So you multiply this one and then divided by what? A n minus 1. So we divide by this one. And this will be the next entry, and this entry will be equal to what? B1. So this is our new entry. Similarly, uh, what we have to do? We have to multiply by the same procedure. So how the same procedure? Remember that this first entry of the row will be multiplied with the succeeding entries. In the previous case, we just multiply this with this one and this one with this one and then divided by this one. Now for the next entry, this will be multiplied with this one and this will be multiplied with this one. You see this one and then divided by the same first entry. So it will continue. It will continue. So you will get this one will be equal to the next entry will be equal to what? Sorry, it is not in the proper order. So you can make it in the proper order by making this B1, and then let's say that the next entry is equal to what? Next entry is equal to B2. Sorry, it is here in the same row. This is B2. So B2 is actually equal to what? B2 is equal to a n minus 1 multiplied by a n minus 4 and then minus a n multiplied by a n minus 5 divided by a n minus 1. And similarly, if we have B3, so B3 will be equal to what? B3 will be equal to a n minus 1 multiplied by a n minus 6 minus an multiplied by an minus 7 divided by an minus 1. So you can get B3 as well, and so on. You will get the other entries also. Remember that we will repeat this for what's called all rows in the table. Let me do this with an example. I think it will clear things. Uh, I will do one kind of the example, and then let's say that we got this example. Let's say that we have what? Let's say the denominator polynomial is equal to what? Is equal to is 3 plus 6s plus 12s plus 8. And we are now checking that whether this system is stable or not. So we are creating the table. So let me create the table. So we are creating the table. We started with what? We started with is 3, sorry, is 3, and then is 2. So is 3 is equal to, you see, the coefficient is equal to 1. The coefficient is 2 is, sorry, this is 6x square. 6x square. The coefficient is equal to 6. The coefficient, and similarly, you will go in the same order. If you arrange this one in the descending order, then it will be easy for you. So if you arrange this one in descending order, then just write this one, you see, up, below, see, up, this is below, then this is up, this is below. And if someone is missing, so you can also write that in the form of is, for example, is 0, is 2, which you can also make it equal to 0. So um, you will not confuse with that one. So now this is equal to 12, and this is equal to 8. And since the order is 3, so we can stop over here also. At the end, you can add these two zeros as well. Now we will come to the next row. So the next row, how we will find the next row? The next row, you see, will be equal to S1. How to calculate? You see, this entry multiply with this one, and then this one with this one, and then divided by 6. So 12 multiplied by 6 is equal to 72. Minus 1 multiplied by 8 is equal to 8, divided by 6. So you got this one, and if you simplify this one, you will get what? 64 divided by 8. Now the next entry will be equal to, you see, 6 multiplied by, the next entry is what? The next entry is 6 multiplied by 0, and then 1 multiplied by 0 divided by 6. So 6 multiplied by 0 is 0, and 1 multiplied by 0 is also equal to 0. So this is equal to 0 by 6. So that is the second entry. We see that 0 by 6 will be equal to what? Is equal to 0. Now we'll come to the next row. The next row will be equal to is 0. We'll come with the same procedure. This time the new entry is equal to what? 64 divided by 8. So 64 divided by 8 multiplied by 8. This one. You see, I earlier told you that we'll go with the same procedure. Let me change this one. So this multiply by this one. Similarly, 6 multiplied by 0. 6 multiplied by 0, and then divided by 64 divided by 8. So what actually we are doing? We are doing 64 divided by 8 multiply by 8 minus 6 multiplied by 0, because this one is 0, and then divided by 64, the first entry. You see, 64 divided by 8. So this straightforward, this is equal to 0, and this one 64 divided by 8 will cancel out, and finally you will left with what? You will left with 8, and then this is equal to 8, and then is equal to 0. So this is how we create the table, and we will use this procedure to create the table in the the coming sections as well. So you should practice on this one, and once you practice on this one, then you will easily understand that what is the this table. In this table, now the table formatting, and you see the manipulation, this the mathematical operation with the table is straightforward. But the most important thing is how to interpret the entries in the table. So we will be doing this interpreting the Routh table, which is very important, because interpreting the Routh table will give you the stability information. So in generally, the Routh stability criteria state that the number of the poles in the right half plane is equal to the number of the sign changes in the first column of the Routh table. So we will look for all possible sign changes, that whether there is any sign change in the first column or not. So if there is one sign change, we can say that one pole is lying in the right hand side and the system is unstable. If we have two sign changes, this means two poles are lying, and so on. So the number of the poles in the right half plane will be equal to the number of the time the sign will change in the first column. So you see in the first column, if when we in the first two rows, you see from here to here, if we will move, there is no sign change, both are plus plus. So if you go from here to here, you see 6, and this is plus, and this one is also plus. If you go from here to here, this is also plus. So actually first is plus, the second value is also plus, the third value is also plus, and this one is 0 is also plus. So you see all are positive, so there is no sign change. This means that there is no pole in the right hand side. So right half plane, no poles in this case. There is no pole in the right half plane. But in case if we have the sign changes, for example, let's say that we have this table started with is 6, then we have is 5, then we have is 4, then we have is 3, is 2, then we have is 1, and finally we have is 0. Let's say that we have plus 6 as the first entry of the row, then we have plus 5 as the second entry, then we have plus 2, then we have plus 1, similarly plus 2, then we have plus 3. I'm just roughly writing this just to show you the plus and negative sign effect on the right hand poles. Plus 1. So you see in this case, you see the sign is not changing. So if there is no sign change, what does it mean? This means that the all poles are lying in the, so all poles are in the left half plane, and the system is stable. Uh, Continuing this one, let's say that we have what we have is 4, we have is 3, we have is 2, then we have is 1, and finally we have is 0. But this is equal to plus 6, then we have plus 5, then we have minus 3, then we have plus 2, and then we have minus 1. Now there are some changes again in this example, and let us interpret this. So you see that from here to here there is 0 changes. From here to here there is 1 change. From negative to positive again there is 1 change, and again from positive to negative there is 1 change. So there are 1, 2, 3, 3 times, total 3 times the sign change. And this means that how many poles are there in this of this system? So the order of the is 4. So this means that we have total of 4 poles. So out of 4 poles, out of 4 poles, how many times the sign change? 3 times. 3 are in the right half plane, and only 1 is in the left half plane. Since there is pole in the right half plane, so quickly we can say that this is an unstable system. So interpreting the what is called the Routh table is very important. So far so good. This will give us only the uh, what is called This will give us only the information when the poles are in the real axis. But what will happen to the some special cases are when the poles are in the imaginary axis. You see, also the information when we get the first entry at the 0. So this is the first special case. Let us discuss this first special case. Let's say that you see special case. What special case with 0 in first column. See, if we get the 0, first column entry, you can say entity. So the first entity is what is 0. So in this case, what will happen? Suppose let us consider the example, and the example is what? The example is g of s is equal to 10 divided by transfer function, which is equal to 10 divided by ds, and ds is equal to what? Let me write on the ds. Let me write this ds in the next page. Let's say that 10 divided by ds, and let's say that ds is equal to what? Is 5 plus 2 is 4 plus 3 is cube plus 6 is square plus 5 is plus 3. So this is the transfer function of the system. You see 10 divided by ds, and we already wrote the value of the ds, denominator polynomial ds. And we see that whether this is a stable system or not. So we will quickly analyze this one to check whether it is a stable system or not. So let us make the initial table. So if you will write the initial table, so initial table, so you will get what? We start with S5, and then S4, and then we come to S4. This is equal to 1, then we have 2, then we have 3, then we have 6, we have 5, and then we have 3, and finally we can add these two zeros for calculation. So the next row is what? Is S3. S3 can be found by doing what? You see, I will repeat again one time, and then I will not repeat these calculations. So this multiply by this one, and this multiply by this one divided by 2. So this will give us the is 3. So if you 2 multiply by 6 and this multiply by this, so you get 0. And similarly 2 multiply by 5, see this multiply by this, and this multiply by this divided by 2. So this will be equal to what? 2 multiplied by 5 is equal to 10 minus 3 is equal to 7 divided by 2. So the next entry is 7 divided by 2. And similarly, if you multiply this with 0, so this will be equal to 0. So you can fill the other entries as 0, 0. Now you see that now we get the 0. Now we get 0, and we have to divide with this first entity every time. See from the previous example you can see. So if you will divide this by 0, you will get the infinity. You will get no solution. So in this case, what we do, we introduce a new parameter, and let's say that this new parameter is equal to what? We replace this first 0 with some e, or a, b, c, whatever value, and let's say that this e is very small value. Let's say is equal to 0.001. That in this case, so we have e, we replace the first entity with e, and then we repeat the other 7 by 2, and then we have 0, 0. And now let us continue with is 2. So is 2, again this multiply by 6, and 2 multiply by 7 by 2. So you will get 6e minus 7 divided by e. And if you want to multiply this with 3, then you see this will be equal to 3e, and 2 multiplied by 0, so this will be equal to, this next entity will be equal to 3e, and the other will be equal to 0 0. We got this one. Similarly, we come to uh, s1, and if you find x1, so it will be equal to, from the calculation it will be equal to 42e, sorry, 42, let me write again, this will be equal to 42e minus 49 minus 6e square divided by 12e minus 14. Remember this, you can easily do by calculation and not by some direct method, and the other will become equal to 0 0. And finally we have, what we have is 0, and if you will multiply this expression with 3e and then divided by this one, so finally you will get sorry, this is 3, uh, this is 3, so you will get what, this is 3, because you see, let me go back to that point. This is the next value is 3 because e multiply by 3, and then we have 2 multiply by 0, which is equal to 0, so 3e divided by e, so e and e will cancel out, so we'll left only with e, and finally we have is 0, which is equal to 3. And now let us see that how many times the sign can change for the very small value equal to 0.001. So the first one is positive, the second one is positive, the third one is E, is still positive. Whatever is, even if it is small value, so it's positive. But the this value, if E is 2, if E is very small, so you can see you will get a negative value over here. So you have negative value over here. Similarly, you have to calculate this one, but you see e square is small, so this is very small, so you can ignore this one. And here also negative divided by negative, so you will get a plus value over here. So easily you can do this one, and finally you get a plus value. So let us see that how many times we change from plus to negative. So you see that let me use another mark. This one. So this is plus. You see, this is plus, this is minus. You see, now there is one change, so I write it one change. And again, there is another change, so I write 1. And then there is no change. So no change is 0, and if there is a change, it is represented by 1. And finally, you count it. So if you will count it, so you will get 2. You can simply add. So this means that S5 has 5 uh, poles. You see the power of is 5 over here. So this system has 5 poles. Out of 5, since there are 2 changes, so 2 poles are in the right half plane. So let me write over here. So S started with S5. So we have 5 poles total. Out of 5, since 2 times the sign change, 2 sign changes, which means that the 2 poles are in the right half plane, and the rest of 5 minus 2, which is equal to 3 poles, are in the left half plane. So it quickly gives us the analysis whether it is a stable or unstable system, and the question over here is whether it is a stable or unstable system. Since the pole lie in the right half plane, so we can say that this is the unstable system for the feedback system. So you see that quickly you can analyze the system. The next one is if we are getting this there is another method for this one also, and that is called reversing the coefficient method. reversing the coefficient method. You see that if you get the first entry as equal to 0, we use a small value. But what will happen if we will reverse the coefficient of the original matrix, this matrix, and then find that whether there is any positive change or not, and why this reversing the coefficient method. So this is also valid. This method is called reverse coefficient method. In this method, the original denominator polynomial d of s with s coefficients is written in the reverse order. Now, the method is derived from the fact that a polynomial that has the reciprocal roots of the original polynomial has its roots remain in the same left half plane or the right half plane or in the imaginary axis. Half. Let's say that let me show this with a small example. And the small example have, let's say that we have the roots which is equal to what, -2 plus minus j3. If we say that which kind of the system is this one, so you can look at the poles, see -2, and then on the imaginary axis we have what, plus j, and then we have 3j, and this is minus 3j. So you see one pole is here and one is here. So from the analysis we can easily say that the poles are in the left half plane. So this is a stable system. And remember that we said that the poles are in the left half plane. Now let's say that we are changing the coefficient, we are reversing the coefficient and see that it remains in the left half plane or not. The poles location will change, but the information that the poles are in the left half plane or the right half plane, we are interested in that information because the objective of the route table is to get the information about the number of the roots present on each side of the S plane. Remember the main objective. So the main objective, we write here main objective, main objective of the route table is to get the information about the, you can say the number of the roots, number of roots present on any side of the S plane. And remember this, let me write with this red one for you, and not the exact location of roots. Remember, the root locus is not giving you the exact location of the roots, but it is giving you only the information that whether the roots are available in the left half or the right half. So we can use that information that whether it is available in the left half or the right half then. So as stated in this example, we say that the roots are in the left half plane. So now let us reverse the coefficient and see that where the roots are available. So in this example, we say that is equal to -2 plus minus j3. And how to reverse? Let's say that this is equal to now d. And if you will reverse, then it is equal to 1 over s. And even 1 over s will be equal to 1 over -2 plus minus j3. And you can multiply and divide with the complex conjugate term, and if you multiply and divide by multiplex conjugate, then this will be minus plus J3 divided by divided by minus 2 plus minus J3 multiply by minus 2 minus plus J3. So D will be equal to minus 2 minus plus J3 divided by, if you multiply this one, so it will be equal to 4 square plus 9 square, and this will be equal to, D will be equal to minus 2 minus plus J3 divided by 97. So just the magnitude of the what is called the real axis and the imaginary axis kind of will be reduced by 97. But you can, if you plot this one again, you will see that D in the D plane or in this plane. So again, the poles are at minus 2 divided by 97, and then we have 3 divided by 97 on the imaginary axis. So the poles remain in the left half plane. So the poles are not changed. So the poles remain within the left half plane. So that is why this method is you see of reversing this method is called the is derived from the fact that the polynomial has the reciprocal roots of the original polynomial, has its roots remain in the same left half plane, right half plane, or on the imaginary axis. So we will continue with the previous example, and the previous example is that so this means that if we have the original polynomial, what we have to do, we have to only what is called we have to what is called um, repeat the polynomial with reverse order. So the coefficient will be the polynomial will be written in the reverse order. How? For example, if we have the same polynomial, let's say that we have a n is power n plus a n minus 1 is power n minus 1 plus a n minus 2 is power n minus 2 plus we have a 2 is 2 plus a 1 is plus a naught. So what we have to do? We have to uh, we have to find the reciprocal of the. So the new polynomial, will be equal to what? S is equal to 1 over d. So you have to write that one. S is equal to 1 over d. So if we just proved that if you will take the reciprocal, so it will remain within the left half plane. So if you take that one, you derive this one a n, and then 1 over d power n plus a n minus 1, 1 over d power s minus 1 plus, then we have a n minus 2, 1 over d power n minus 2 plus the same fashion. So you can say a 2, 1 over d square plus a 1 over d, and then we have a naught. So if you multiply this expression with dn, so if you will multiply with dn, then the new polynomial will become equal to what? Let's say that this is p, the new polynomial represented with p. So the new polynomial will become equal to ps. So the new polynomial will become equal to what? A naught dn plus a1 dn minus 1 plus a n minus 1 d plus a n. So we just reverse the coefficient of the original polynomial. So this means that if we have the original function in the previous example, we state that g of s is equal to 10 divided by the denominator polynomial, and then we say that the denominator polynomial is equal to s power 5 plus 2 power s4 plus 3s cube plus 6s square plus 5s plus 3. And when we solve this one in the previous case, um, in this case, you see, we got a 0. And then we introduced this new entity. So we stuck with over here because we cannot continue with this 0 over here. We cannot continue with this 0 over here. So what we did, we introduced that small entity. But now we are not interested in small entity. We are going to replace the original function with the reverse. We are going to write it in the reverse order. So if we write in the reverse order, so the new polynomial will become equal to what? P of s. And now we started with this one. So this will become equal to what? Um, uh, just, you see, change the coefficients. The highest coefficient is equal to what is called the highest order is 5. So we can write this one is equal to 3. 3. So instead of this one, so we just reverse this one. See? So this will become equal to 3 is 5 plus 5 is 4 plus 6 is cube plus 3 is square plus 2 is plus 1. We write the expression with the original denominator polynomial with its coefficient is written in the reverse order. So we just write the original polynomial in the reverse order. Now we have to find the what is called the table for this one. So if you write the table for this one, you will get what you will get is 5, then is 4. So you see that 5, 4, then 6, 6, 3, and then 2, 1. So we write in that fashion. So 3, 5, 6, 3, 2, 1, and then you can also write 0, 0. And this we will check whether it is plus or negative. So how to do the next entry? The next entry will continue with this one, 5 multiplied by 6 minus 3 by 3 divided by 5. So if you will do that one, so is 3 will become equal to 4.2. Similarly, 5 multiplied by 2 minus 3 multiplied by 7 divided by 5. So this will be equal to 1.4. And then we have 0, 0. The next entity will become equal to a square. This will become equal to this multiplied by this one minus 5 multiplied by 4. And if you do this one divided by 4.2, so it will become equal to 1.33. And similarly, 4.2 multiplied by this one minus 5 multiplied by this one. So if you will do that one, um, you will get the answer equal to this is 1.33. This will be equal to 1, and similarly this will be equal to 0. If you will continue in the same order, so you will get is 1, and this will be equal to minus 1.750, and then we have 0. And similarly, finally, we will got 0. This will be equal to 1, 0, 0, 0. Now let me come back to the original problem and then come the first method. In the first method, we said that there is two sign changes. You can notice this one. There are two sign changes, and we said that there are 2 poles that are in the right half plane, and the rest of the 3 poles they are in the left half plane. So in this one, please check that if we use this reverse method, reverse coefficient method, again you see the sign of the 3 is plus, the sign of 5 is equal to plus, the sign of 4.2 is what? Is plus, sign of this one is plus, sign of this one is negative, the sign of this one is plus. So this is plus, this is plus, this is plus. Then we have a negative, so this is 1. And then we have a positive from negative, so again this is 1. So you see that how many times the sign changed? 2 times. So in the right half plane we have 2 poles. In the left half plane 5 minus 2 poles. The rest of the poles will be in the left half plane. And since there are poles in the right half plane, so we can say that this is an unstable system. So this is the case when we got the first entity as equal to 0. But the problem still lies, and that is what will happen if the whole what is called the whole row is equal to 0. So if the whole row is equal to 0, so even the reverse problem will not solve the, the, the original problem. So this means that the method discussed earlier for the special case in which only the first element of the row is 0 will not help in solving the special case with all elements of the row equal to 0. So we can have this, we will introduce the new method which is called the auxiliary polynomial method. And why? Let's say that we have a polynomial of order sk. We have this table. So we have sk, and then we have s our k minus 1. So this is a k, this is a k minus 2, and then we have a k minus 4. And this is equal to 0, 0, 0. So you see in this case the complete row is equal to 0. So even if you will reverse the polynomial, it will the coefficient of the polynomial will not help. If you replace the first entity by a small value, still it will not help, because the succeeding will also become equal to 0. So this the previous method will not help. So now we have to introduce the let's say this is equal to a k minus 1, this is k minus 2. So this is a k minus 1, this is a k minus 2. So let us use a new method which is called the polynomial method. What will happen? So the row above this 0, row, this row above the 0 row, we have to find the polynomial of that one. So the polynomial of this one is equal to, you already know what is the polynomial of this one. The polynomial of this one will be equal to what? A, this is the coefficient, and the s power will be equal to sk plus a k minus 1. This is the coefficient, and the s power will be equal to what? You see, it will reduce by 2. You see, because sk, then k minus 1, this k minus 2, and so on. Remember that procedure. So this will be equal to k minus 2 plus a k minus 2 is k minus 4. So we have the auxiliary polynomial, and um, now we are going to find the um, now we are going to replace the row of 0 with the coefficient of the differentiation of the auxiliary polynomial. So we have the auxiliary polynomial. We are going to find the dp over ds, and then replace the row of 0 with this dp divided by ds. So we are going to replace this one. And then the most important thing is the interpretation of the what is called the Routh table. So we will interpret the Routh table as also, because that is the most important thing. Let us continue with this example, and then we'll come back to the interpretation later on. The example is, let we have the transfer function with the denominator polynomial equal to what? Is equal to is 5 plus 7 is 4 plus 6 is cube plus 42 is square. Then we have plus 8 is plus 56. So straightforwardly, we are going to create the Routh table. So if you will write the Routh table, so we started with is 5, then we have is 4. So we have 1, then we have 7. This is 1, 7. Then we have what? Then we have 6. Then we have 42. Then we have 8. And then we have 56. Then we have 0, 0. So we got this one. So let us find the new row. The new row is 3. And 3 can be found by multiplying this one, and then so 7 multiplied by 6 is 42, minus 1 divided by 42 is also equal to 42. So 42 minus 42 will be equal to 0. So this is 0, 0, and the rest is also equal to 0. Now this happens when the two, you see, the two rows that are identical. You see, if you will divide this row by 7, because 7 is the common in this row. So if you will divide this by 7, so you will get this is equal to 1, this is equal to 6, and this is equal to 8, which is identical to the first row. So this row and this row is identical. So if the two rows are identical, then what will happen? Then you will get the new row will be equal to 0, because then multiplication, and then you see there is subtraction. So the same entities are subtracted, so it will become equal to 0. So now what will happen? So just above this row we have which row? We have this row, and this row is now equal to what? PS, because we said that the auxiliary polynomial will be equal to what? The row above the 0 row. And if you will take 7 as a common from this row, so this will be equal to what? You can take 7 common also, so it will simplify the things. So divide every term by 7, so this will become equal to 1, this will become equal to 6, this will become equal to 8, and this will become equal to 0. So this row will become equal to what? 1 is 4 plus 6 is square plus 8 plus 8 is 0. So we stop over here. So you can write is 0. So we stop over here, and now you can see that we have this PS, which is equal to is 4 plus 6 is square plus 8. So we got this polynomial. We are going to find the differential of this polynomial dp over ds. So this will be equal to uh, 4 4 is cube plus 12 is plus 0. So we got what? We got the new polynomial, which is equal to 4 is cube plus 12 is plus 0. And now we are going to replace this this row with the coefficient of this auxiliary polynomial. So let me repeat over here. So we have is 4, and then we have is 3. So this is equal to 1. Is 4 is equal to what? Is 4 is equal to 1680. So let me write this one, 1680, and S3 which was equal to 000. So we replace this with the auxiliary polynomial coefficients, and that is equal to what? That is equal to uh, 200. So we have 2000. So we replace with this one. You see this one. Sorry, this is equal to what? This is equal to 4120. Sorry, this is equal to 4120. So let me write this one is equal to 4120. and 0. So this is equal to, let me erase this one, this is equal to 4, 12 and 0, 0. So now the next row is equal to is 2 will be equal to 6 multiplied by you see uh, see 4 multiplied by 6 minus 1 multiplied by 12 divided by 4 will be equal to what? 12 divided by 4. You see 4 multiplied by 6 minus 12 divided by 4. So this will be equal to 24 minus 12, which is equal to 12 divided by 4. So is equal to what? Let me use the direct answer, which will be equal to 3. Similarly, for the other entities, 12 multiplied by 4 multiplied by 8. So divided by 4. So this will be equal to 8, and then we have 0, 0. Similarly, we have S1. S1 will become equal to 3 multiplied by 12 minus 4 multiplied by this one. So it will become equal to 1 by 3. And then we have 0, 0, 0. And finally, we have S0, which will become equal to this multiplied by this one minus 3 multiplied by 0, which is equal to 0, divided by this one. So it will become equal to 8, 0, 0, 0. Now, the interpretation of this is very much important. Remember that the auxiliary polynomial will introduce the imaginary poles. So, and they will be symmetric. The imaginary poles and they will be symmetric. So, the symmetry can occur under the three conditions. The poles are symmetrical and they are on the real axis. You see, they can be on the real axis. So, the auxiliary polynomial, the poles will be on the real axis, and the symmetric. They can also be, you see, symmetric on the imaginary axis, or they can be on the this quad. This is called the quadrantial poles. These are called the quadrantial poles. Anyways, the poles will be the imaginary poles, and it will be symmetrical. It will be symmetrical. For example, in this case, what we have. First of all, the sign, you see the sign. So we will look for the sign. So if you write S5, which is also equal to 1, 6, sorry, that is also equal to 1, 6, 8, and 0. So first of all, we will look for the sign changes. So this is plus, plus, and you see all are plus. So there is no sign change. So this means that there is no pole in the uh, right hand plane. So there is no what is called, there is no pole in the right half plane. Why? Because there is no sign change. So we have to notice that one. The second thing is that before the auxiliary polynomial we have only one pole, because the order of the auxiliary polynomial is 4. So PS has an order of what? Is 4, and the order of the ds is equal to what? 5. So the number of poles initially will be equal to what? Is 5 minus 4. So this was the initial number of the poles, and since initially you see that there is it is positive, the first pole, so it is in the left hand plane. So this one pole is in the left half plane. Remember this one. Now the order of the auxiliary polynomial is 4, which means that we have 4 imaginary poles. We have four imaginary poles. Remember that the auxiliary polynomial, as I said earlier, will introduce the imaginary poles. So here we have the 4 imaginary poles. First, we will look for the sign change. So you see that there is no sign change, which means that the four poles which will be in the left half plane. So these 4 poles, imaginary poles, these are in the left half plane. Why? Because no sign change. So there is, you see, you did not see any change of the sign from positive to negative and negative to positive. This means that all poles are in the left half plane. So this information is sufficient to know that whether the system is stable or not. Anyhow, if you are interested in the pole location, you see information, we see that the poles, they are imaginary and they should be symmetrical. If we have the imaginary poles, remember, if we have the imaginary pole 1, so it has a symmetrical partner over here, same location but on the negative imaginary axis. So this means that we have the 4 poles, but they are at the imaginary axis, and 1 pole is along the left half plane. The location is not known, but if it is 1 pole, it has no symmetrical another term. So if it has no symmetrical term, this means that it is along the real axis. So we should know about that one also. So in general, the Routh stability criteria give us only the information about the poles, whether it is laying in the left half plane or the right half plane. To summarize this one, this auxiliary polynomial, let's say that we have the complex variable, which is what let the denominator polynomial of the GS is equal to this one. And this is another example. So let us explain this another example, and then we will finish up with the today's class. Let's say that ds is equal to s4 plus s cube minus s minus 1. So we are going to find the Routh table for this one. So if you find the Routh table for this one, then we have what we started with is 4, and then is 3, and then it will be equal to what, 1 1, and then is 2 is 0, is 3 is minus 1, and then this one is equal to minus 1, and then we have 0. So we got this one. If you go to the S2 by simplification, so by using the same creating the new row, so we see that it will be equal to 1 minus 1 and 0. And here we stuck because we got the 2 rows that are same. You can check. You see this row and this row, they are same. So here we have to do what we have to do, introduce the auxiliary polynomial for this row. If you get the new row, of course, if you get the new row is 1, so it will become equal to 0 0 0. So this means that we have to replace the coefficient of this with the coefficient of dp over ds. So the question is, what is p of s? So p of s will be the coefficient of the row above the 0, and which is equal to square minus 1 in this case. And if you want dp over ds, so it will be equal to what? It will be equal to 2s plus 0. So this means that we have now to replace the coefficient of this one with this one. If you replace this one with the coefficient of this one, so s1 will become equal to s1. You can say s1 new. S1 new will become equal to 2, and then we have 0 0. Similarly, if you will go to the is 0, so is 0 will be equal to what? 2 multiplied by 0 is 0, and this will be equal to again no, sorry, 2 multiplied by minus 1 is equal to what? Minus 2 divided by 2, so you will get what? Minus 1. So you get minus 1, and then we have 0 0. Now let us look for the changes. So initially you see this is plus, this is plus, and then again we have plus, and then we have auxiliary polynomial with plus, and then we have this negative. So we have only one sign change. So you see one sign change after the auxiliary polynomial. So after the auxiliary polynomial, there is one sign change. So there is one imaginary. So there is one imaginary pole. One imaginary pole. And if we have one imaginary pole, this means that this imaginary pole will be in which side? The auxiliary polynomial. So we have one sign change, one imaginary pole in the right half plane. So this means that in the right half plane you have one pole. There is no other partner of this. You see symmetry of this one imaginary pole. If there were two poles in the right half plane, it should be like this. But since there is one pole in the right half plane, there is no other location except the real axis. So there's one pole is lying in the real axis. But since this has it should have the symmetry, and for symmetry, one pole should lie on the real axis in the left half plane. In the left half plane. So because the auxiliary polynomial will give you the symmetrical and the imaginary pole. So the symmetry and the imaginary condition is satisfied. Now let us go to the original polynomial. And the original polynomial, you see up to here, up to this is 2. There is no sign change. So this means that is 4 minus is 1, which is equal to 4 minus 1. 4 minus 1, which is equal to 3. So 3 poles are in the left half plane. So total we have how many poles? Total the power of S is, the order of S is 4. So total we have 4 poles. 4 poles. One is in the right half plane because we have the auxiliary polynomial and we have only one sign change. One sign change. So one pole is in the right half plane, so the rest of the 3 is in the left half plane. Left half plane, so we have the 3 poles. Now, along the left half plane, we see that due to the symmetry, one pole is along the real axis. From these 3, you see one is along the real axis, and since there is this auxiliary polynomial, so there should be some symmetric, what is called, all poles should be symmetric. So this means that we have some symmetry along the left half side also. So we have 2 plus 2, what is called complex, you can say imaginary, 2 poles along the imaginary axis. So it can be anywhere. It can be like this and this one. So you see, so we have the 2 symmetrical poles. One pole is along the real axis in the left half side, half plane. So we have total of 3 poles in the left half plane, and one pole is along the right half plane due to the sign change. And from this now we can conclude that you see, we conclude that the auxiliary polynomial actually introduced these symmetrical poles. So that is why we know that these 2 poles, one and these 2 poles, they are symmetrical. And we also know that this pole and this pole, they are at same distance from the origin. From this origin, they are same distance from the origin, and they are symmetrical, but they are in the different planes. Since there is a pole in the right half plane, so we say that this system is not stable. So you see that we can easily find analyze the system to find stability, whether it is a stable system or unstable system or marginally stable, if we can correctly use the Routh stability criteria. Within the Routh stability criteria, interpreting the Routh table is very much important. Without interpreting the Routh table, you do not know the exact information about the system. Also, there are some 3 conditions. So if we get 0 in the as an entity in the row, the first entity, so we can introduce the small variable, the small coefficient e. We can also reverse the coefficient of the polynomial, so which can avoid this division by 0. In the third term is if we get case, special case is if the complete row is 0. So in that case, you see both earlier cases will not help. So what we have to do is to find the differentiation of the auxiliary polynomial, which will be the coefficient, which will the auxiliary polynomial, which have the coefficient of the row just above the 0 row. We have to find the differentiation of that one, and then replace the 0 row with the coefficient of the differentiation of the auxiliary polynomial, and we should continue with this one. But the auxiliary polynomial will introduce what? This will introduce the symmetrical and the imaginary poles. So you should keep that one, that if we have only one pole in the along the right hand side with one positive change, one pole, if we have see three changes, so this means that now we have one pole along the real axis and the two along the imaginary axis. And then we have the symmetrical, what is called symmetry, also on the left hand side. So but if we have only one change, so this means that the you see one pole, it has no symmetry along the imaginary axis within the same half plane, so it should be on the what is called the real axis. But in all this procedure, you see that we do not know the exact location of the poles. So we only analyze the system whether it is stable or unstable system. Thank you very much. Take care of yourself. Inshallah, we will meet in the next session. Allah Hafiz.